Esse seminário é uma continuidade, né, da disciplina de seminários e a primeira palestra do nosso programa de Altos Estudos, que é um programa da CAPES, um projeto da CAPES, que nós fomos contemplados juntamente com o programa de Zoologia, Entomologia e da Universidade de Maringá, curso de Ecologia deles, da Universidade de Maringá. Então nós estamos começando o nosso projeto, né? Então o nosso palestrante, o professor Ian Brooks, Walter vai fazer a apresentação. E, então, essa palavra para ele.
Eu não sei, eu não posso expressar o prazer de ter o professor Dan Brooks aqui no nosso curso. Curiosamente, eu acho que ele foi a primeira pessoa que eu convidei para uma palestra como pessoa, né, quando eu estava na Universidade de Idaho. O professor Brooks, eu acho que fica muito claro o currículo dele, eu não preciso falar muito sobre o currículo, porque ele está online, se vocês quiserem dar uma olhada, são só 240 trabalhos, 44 livros, etc. Mas, principalmente, ele é uma das pessoas que fez diferença na área de filogeografia, taxonomia sistemática e, principalmente, em ecologia e evolução. Então, ele iniciou novas linhas de pesquisa, ao ponto de hoje a gente ter centenas e centenas de pesquisadores trabalhando em linhas que ele iniciou, como, por exemplo, a filogeografia ou a biogeografia da invasão de animais marinhos no ambiente aquático continental da América do Sul, a filogenia, filogeografia e biologia de crocodilianos e seus parasitas, e principalmente eu vejo o professor Brooks como sendo a interação, que alguns de vocês já sabem que eu falo tanto, sobre a parasitologia verdadeiramente biológica e evolutiva com a ecologia, né? E ele foi uma das pessoas que introduziu o conceito de ecologia histórica, que vem já sendo amplamente usado no mundo inteiro, nem tanto quanto deveria ser, e por isso ele está aqui para falar com a gente. Dan, thank you for your presence, and I think we're going to have fun on these next weeks. So you got the...
Well, thank you very much. I apologize for not being fortunate enough to be able to speak Portuguese. But I do speak Spanish, and so in some way we'll all be able to communicate. Most of you, especially the youngsters, English is everyone's second language now, so we're probably, because it's the Swahili of the internet. But I'm very honored to be here, and I need the microphone. And I especially want to thank Walter for the very kind words. Normally you don't hear words like that when you're still alive, so thank you very much. I'm very grateful. Now, next week, and the next week here, and then the week after that in Maringá, I'm going to be giving a series of lectures that will be more technical, more recognizable as biology, as science, as something we do. Now, most of you spend a lot of time working with various kinds of hardware, sequencers, computers, microscopes, all kinds of software. But today's lecture is going to be about the third part of science, which science fiction writers like Peter Watts call wetware. That's us. And the most important thing about science is still this. And the most important thing about concepts in science is still our imagination and our creativity. So while it's important to generate a lot of material observations, do a lot of very close technical analyses of data, it's still very important, it's crucial for science for us to have good ideas. And what I want to talk to you about today is one aspect of something that seems to be emerging now, which is a new view, a new perspective on evolution, which many people are calling the extended synthesis. And I'm not going to talk about what we call this, what the name is going to be, because that's mostly sociology. What I'm going to talk to you today about is one way to try to organize your own thinking about many different perspectives that you're going to read in the next few years. Because now that people have decided that we need this new evolutionary biology, of course, there are many people who want to be the person. And so many people are going to be writing articles saying, this is the way to have the new evolutionary biology. And the new evolutionary biology will always involve citing a lot of their own papers. And my perspective is that what we want for a new biology is something that is much more inclusive, much broader, that actually allows people from many different specializations to talk together. And as a consequence, what we need is not technical language or nomenclature. What we need is more metaphorical language to try to give us a framework for talking about many different concepts and a lot of different kinds of data. And so that's why I've titled this presentation Children of Time, which is my metaphor for organisms and species. Darwin called species communities of descent. And Children of Time is the same idea. Now, the reason I've been preoccupied with metaphors for the last 4 or 5 years is because even though most scientists don't think about this directly, it is true that metaphors are always essential whenever a theory is being changed. We will always use metaphors to change or try to convince people to change their perspectives. And the reason for that is because metaphors allow us to use old vocabulary to refer to new ideas and new concepts. And they also allow us to bring new basic observations into an old framework. So metaphors are a linguistic bridge between the old and the new. And in evolutionary biology, especially in terms of my particular prejudice about evolutionary theory, this is essential because I believe that because metaphorical thinking allows us to not worry about space and time in the real world, they allow us to suspend the rules of space and time. And I think that's essential now because I believe that this new evolutionary synthesis has to be extended back to before neo-Darwinism, and then it has to go beyond neo-Darwinism. So I'm going to make a statement that will make many people uncomfortable, if not angry, and that is I'm going to say that while we learned a lot about biology and a lot about evolution during the time of the new synthesis, during the time of neo-Darwinism, neo-Darwinism was a big mistake. We lost more than we gained. The costs were greater than the benefits. Fortunately, we have Darwinism to fall back on. So we haven't lost everything. We have just lost some time. So now I'm going to talk about Darwin's metaphors. Now, normally, when people talk about Darwin's metaphors in a biology class, you talk about natural selection and then you just move on. But Darwin's view of biology and view of evolution was much deeper, much broader, much richer, much more panoramic. And this is from the second paragraph of the first page of the first chapter of Origin of Species. And here he says that evolution involves 2 factors. And natural selection is not one of them. So one factor is what he called the nature of the organism, and the other is what he called the nature of the conditions. And interestingly enough, not only did he identify 2 different factors in evolution, or that work together to produce evolution, he said that one of them is more important than the other. And it was not the environment. It was not the nature of the conditions. It was the nature of the organism that Darwin said was more important than the nature of the conditions. And that's because, in part, Darwin was trying to make a clear distinction between his views and the Panglossian adaptationism of Lamarck. And we'll show how this works. So here's what Darwin thought was in the nature of the organism. In other words, this is what comes packaged. These are the capacities of all organisms. They are capable of overproducing offspring. They're capable of producing more offspring than there are resources to support them. And this is our insight into the notion that reproduction is very cheap. It's not very costly. The offspring are variable, but they're also historical in the sense that offspring of single parents or members of the same species resemble each other more closely than they differ, even though each individual has some unique features, the vast majority of the traits are shared. And organisms are also able to act in their own behalf. That is, they're able to do things to try to survive. And that, all of this occurs regardless of the environment. All organisms have this no matter where they are, no matter what the environmental conditions are. Now Darwin, as you know, Darwin recognized a paradox, the paradox of Malthus, which is that biological systems produce more offspring than there are resources to support them. And he asked whether or not this could exist in a Panglossian world, in a Lamarckian world, where everything fit perfectly and everything adapted itself perfectly. And he said, no, that cannot happen. You cannot have organisms that are unable to survive in a world that's perfectly, a world of perfect adaptation. So there must be some constraints on the response to these surroundings. And he said that it was actually the nature of the organism that created the constraints. That organisms are not infinitely capable of adapting to their surroundings. So it's actually the insensitivity of organisms to their surroundings which actually produced this mismatch between the organism and the environment. And the degree of that mismatch, the degree to which organisms do not fit their environments perfectly, is proportional to the strength of this emergent property called natural selection. So this is where natural selection came from. Natural selection is an emergent property of the autonomous nature or semi-autonomous nature of the organism. So this is Darwin's paradox, the way to have Darwinian adaptation sensitive to their environments. And that's very different from the Lamarckian view. It's also very different from the neo-Darwinian view, as I'll suggest. Darwin had a higher law. Now this is later in the book. And most historians of biology, most philosophers of biology, say that this statement identifies natural selection as the higher law. But in reality, the law of the conditions of existence, in the second paragraph of the first page of the book, Darwin identifies the law of the conditions of existence as the interaction of the nature of the organism and the nature of the conditions. So that was Darwin's law. Darwin's law was not natural selection. Darwin never called natural selection a law. It's just real and important, but it's not a law. And in 1905, the physicist Ludwig von Boltzmann, who was, among other things, he was the professor who taught Gregor Mendel statistics. He identified in a public lecture, he called the 19th century Darwin's century, and hoped that the development of statistical mechanics in physics would do for physics what Darwin had done for biology. And he identified the second law. He said that what he thought Darwin had done was to set the groundwork for a statistical mechanical treatment of biology. Darwin had two visual metaphors that dealt with complexity. One of them is the phylogenetic tree. Most of you know that the only illustration ever to appear in any edition of The Origin of Species was a picture of a phylogenetic tree. And the other visual metaphor he had is at the very end of the book, and that's his ecological metaphor. This is more or less his systematic metaphor. This is his ecological metaphor. The tangled bank, this enormous, complex association of many, many species all functioning together in very complicated ways in the same place and same time. Now, very shortly after Darwin's views became accepted, Herbert Spencer, who was a racist sociologist, decided that Darwin's views could be interpreted in a way to explain why the British Empire was the ultimate of human perfection. And he coined a term called survival of the fittest. Now, of course, Darwinism was not survival of the fittest. Darwinism was survival of the adequate. But Spencer had very powerful friends who were also very powerful friends of Darwin. And so in the final edition, the 6th edition of Origin of Species, there is a large discussion. Darwin wrote a large discussion where he says natural selection or survival of the fittest. And there's this long, complicated, confused dialogue or statement by Darwin trying to reconcile survival of the fittest with his views, in which he tries to make the case that the concept of survival of the fittest is not a progressivist doctrine. But of course it was, because Spencer explicitly said it was. It was inevitable that this would happen. And so many historians have interpreted, most historians of biology don't read the 6th edition very much, because they have decided that all the modifications in the 6th edition were Darwin's attempts to be nice to his enemies. But I believe that the only confused thing in the 6th edition was the place where he was trying to be nice to his friends. He was trying to keep his friends happy. And in the rest of the book, if you compare the different editions, the rest of the book is just a statement of all of the new ideas that Darwin had come to in the 13 years since his first edition had been published. And so there's a lot of really good biology. Now, biologists always read the most recent thing. If somebody writes a paper in 1960 and then writes another paper in 1980 and changes his mind, you cite the 1980 paper. It's not really fair to go back and say, well, in 1960 you were wrong. So, oh, yes, and I corrected it in 1980. The same thing with scientists reading Darwin. So I say with friends like that, who needs enemies? Spencer was the founder of Neo-Darwinism. Neo-Darwinism should be called Spencerism. Okay, now, we fast forward from about 1880 to the 1960s, and this is what Steve Gould called the hardened synthesis. And that is the culmination of the refinement of Neo-Darwinian thought, so that both complexity and time could be eliminated from evolutionary explanations. And the first thing we decided as evolutionary biologists was that history played no role in causal explanations in biology. So that eliminates the tree of life. That's why from about 1900 to 1970, you saw no phylogenetic trees in the literature. And that's one of the reasons that phylogenetic systematics was so controversial and so aggressively fought against in the 1970s and 1980s. And then second of all, we ended up with a very simple view of evolution, which said that the nature of the conditions creates the nature of the organism, or function follows the environment and form follows function. And these are very easy little snappy sound bites to remember. You can put them on examinations, get an A. Everything's very simple. But that eliminates the nature of the organism as anything more than just an epiphenomenon of the environment. And as Niles Eldredge pointed out in two of his major books, this completely blurs the distinction. It completely erases the distinction between Darwinian and Lamarckian explanations. Now, the eclipse of Darwinism, now Peter Bowler said that the eclipse of Darwinism began in 1890 and ended with neo-Lamarckism and orthogenesis, and it ended in the 1930s with the emergence of neo-Darwinism. I believe the eclipse of Darwinism began with Herbert Spencer, and it's not over yet. The eclipse only began to disappear in the 1980s, and it began to disappear primarily as a result of the phylogenetics revolution, which represented a new appreciation for the nature of the organism and the primacy of the nature of the organism. So in the 1980s, which was coincidentally the 100th anniversary of Darwin's death, you had a number of proposals by people. Niles Eldredge working with Stan Salta, but then expanding this, also working with Steve Gould, and expanding this perspective, the hierarchical perspective of evolution. based on the notion that you have a genealogical hierarchy and an ecological hierarchy. And organisms, of course, are simultaneously part of both hierarchies. So this is a way to separate parts. This is almost like different terms in an analysis of variance. But notice that the genealogical hierarchy really pertains to the tree of life and the nature of the organism. And the ecological hierarchy pertains to the nature of the conditions and the tangled bank. So as it turns out, while these proposals were considered to be very bad with respect to the current consensus at the time, so neo-Darwinists at the time opposed these ideas greatly, and yet this is just a restatement of Darwin's fundamental law of the conditions of existence. Ed Wiley and I published a book and a bunch of papers in the 1980s, taking a slightly different terminology, a slightly different perspective on this, but in fact we were doing the same thing. We thought that we were in opposition to Darwinism because we believed that neo-Darwinism was Darwinian, and that was our mistake. Because people like Ernst Mayr assured us that neo-Darwinism was just a refinement of Darwinism instead of being a bastardization of it. But again, you see that in fact Ed and I were restating Darwin's fundamental principle. And in the 1990s, John Maynard Smith and Ernst Satmari published a book called The Major Transitions in Evolution. And once again, different terminology, different focus, different perspective, but the same fundamental view of the world. And it's very Darwinian. It's not neo-Darwinian at all, but it's very Darwinian. Now, we jump ahead, and this is why we use metaphors. Now we're going to jump ahead. We're going to jump into today and the near future, where we want to extend the end of the eclipse of Darwinism. We really want to bring Darwinism back and then build on that. And what I'm going to suggest are some metaphors for thinking about the conditions of existence, Darwin's law of the conditions of existence. And these are metaphors that involve some dualism, some dualities in our experience. And one of them is that biologists think of time in two different ways. And these are what Shevik, who is a temporal physicist, and those of you who know the work of Ursula Le Guin and her novel The Dispossessed will know that Shevik was actually an alien physicist in a science fiction novel. But he was a temporal physicist, and he was interested in these two different senses of time. What he called, or what Ms. Le Guin called, simultaneity and sequency views of time. Simultaneity is what we call cyclical time. Now it's called simultaneity because time is always going in one direction, but it always ends up back where it started. So all our physiological cycles are like that. Lunar cycles are like that. Annual cycles in astronomy are all simultaneity. After 1 year, we're back where we started. So if you only look at the first day of the year and the last day of the year, it appears that no time has passed because it appears that nothing has moved. And yet, during the entire period, there has been movement. Now, that's metabolism. And metabolism is actually how organisms make time. That's how biological organisms make time. That's another way of stating the thermodynamics of life. That's what organisms do when they process energy. They're making time. And cyclical time is all about survival and the ecological hierarchy. And the interesting thing about the cost of making that kind of time, the cost of maintaining life, this is like the cost of living. This is really expensive. It costs a lot to do this. And this is all about organisms communicating with their surroundings. It's all about the nature of the conditions. Sequency views, this is linear time. This is all about the flow of information. It's about buying time, not making time, but buying time. It's about persistence and survival. It's about the genealogical hierarchy and the phylogenetic tree, which is the highway of evolution. This is the cost of evolving, and it's very cheap. Now, of course, this is just another very complicated way of saying it's really cheap to produce organisms. It's not so cheap to support them. And that is what creates the mismatch. That's what creates natural selection. It's really cheap to make them. It's not so cheap for them to survive. Now, sequencing is all about organisms talking to themselves. In the 1960s and 70s and 80s, there were many flowcharts like this by people trying to link information theory to biology. And normally, in those flowcharts, you had a genetic system, which was this pool of random variation, which was essential for neo-Darwinism, even though there is no random variation anywhere in the entire biological world. And the molecular biology revolution has really killed that idea. There's no such thing as, if there was really random variation, we couldn't do undergraduate experiments in fruit fly genetics because we could never predict the outcomes. And if we really had random variation, mutation rates would be higher than replication rates. So you have a lot of variability in here, but there's nothing random about this. But the idea was you had all this random variation, then some of it was realized by reproduction, turned into organisms by developmental stuff, and then the organism that was produced was released into the environment, which would then assess it and convert some of those organisms into meaningful information and eliminate the rest. So the idea was that the genetic system was talking to the environment. The reality is the genetic systems, when they reproduce, they talk to themselves. When we reproduce, we're actually talking to our own future. So what organisms do is produce organisms that perpetuate a flow of information. So metaphorically, we're actually talking to ourselves. It's not a different place. It's not as if the genetics is in one place and the receiver, the environment, is in a different place. It's a different time. So the source and the receiver are displaced in time, but they're the same system. And this is the basic philosophy that's used by self-correcting computer programs. All of your system optimization programs, all based on this very Darwinian view. Now, so how do we integrate these two senses of time in biology? Well, what's really cool about this is that Darwin had it. Biologists had known how to do this integration of the duality of time forever. Metabolism allows life to persist long enough to reproduce, to transmit information. Metabolism is how we pay for evolution, but reproduction and the flow of information is evolution. And a visual metaphor for that temporal duality is cyclical time plus linear time gives you what Greek philosophers called the great circle of life, which in Greek was called helix. This is very kind of cool because, of course, they had no idea about the helical nature of DNA and RNA. But that was time to the Greeks originally. Time went in a circle and didn't go anywhere because Cronus, the god of time, the embodiment of time, kept eating his children. So nothing ever went anywhere. And only when that cycle was broken, when Cronus was castrated and released children into the world so that things survived and produced offspring, that was when linear time was released into reality. And that took this closed circle of life and opened it into what the Greeks called the great circle of life. That was their explanation for how to integrate the two different views of time. And that's what we see in biology. And this leads to a distinction, a new distinction between macro and microevolution. Microevolution is not things that happen in small areas on short time scales. Microevolutionary phenomena are things that are reversible. And macroevolutionary phenomena are things that are irreversible, or as the physicists say, microevolutionary phenomena or microscopic phenomena, macroevolutionary phenomena or macroscopic phenomena. Now that means, strangely enough, that means that ontogeny, for example, is inherently macroevolutionary, even though population genetics is microevolutionary. So this is a very different way of thinking of macro and micro. Now there's also a spatial duality in biology. There are two different senses of space that we talk about, one of which is information space, and that's how we think about the genealogical hierarchy, and the other is function space, or sometimes called fitness space. And next week, when I talk about phylogeny and adaptation, I'll explain more fully why we need to distinguish this, because Darwin had two different views. He used the word adaptation in two different ways, one of which, the most fundamental of which, simply meant function. And only a subset of those adaptations, those functions, were actually evolutionary adaptations. The origin of the information space. Well, how do we get a big space full of lots and lots of information and variation? Well, it's in the nature of the organism to reproduce, and to reproduce semi-conservatively. So even though we have a lot of redundancy in the reproductive output, we also have innovation. So it's the nature of the organism to explore all possibilities of all inheritances that are available through time. Now, Ed Wiley and I suggested that biological information space, inheritance space, was inherently combinatorial. And that's partly because DNA is combinatorial, RNA is combinatorial, and the assumption is that what's built on top of that, the hierarchical levels on top of that, are also combinatorial in nature. Now, if that's true, then Eldridge's view that the biological world is inherently hierarchical must be true. If information space is combinatorial, hierarchical structure is inevitable. And our job is not to decide whether it exists or not. Our job is to figure out the different functional levels in the hierarchy and explain them and explain how they interact. Also, if this is true, if information space is combinatorial, then Maynard Smith and Sathmary's assertion that basing reproduction on digital replicators means that evolution is open-ended, that it is potentially, and it is what they call an indefinite process. It's potentially unlimited capacity for producing variation, which is not the same thing as saying that variation is random. It's that there is a lot. Possibilities are enormous. And in fact, evolution itself, the nature of the organism, is capable of producing many, many possibilities regardless of the environment. Now, information space is partitioned into all possibilities and a subset which are the actual, the realized reproductive events. So, for example, horses do not reproduce with rose bushes. But if you have this great big huge space called all the inheritance out there, conceptually you could have rose bushes reproducing with horses. And that never happens. So then we have to provide an explanation for that. The actual inheritances are what we call realized information, and this is analogous to fundamental and realized niche space in ecology. Evolutionary transitions of Maynard Smith and Sathmary are produced by genealogically cohesive innovations, as conservative innovations that increase the efficiency of storing and transmitting information. And that allows actual diversity, actual variation to increase, and potential to increase, and potential to increase even more than the actual. So it is the nature of the organism to produce more potential than actual variation. And this is a way to restate the Red Queen hypothesis. It's not the environment changing rapidly that causes evolution to go fast. It is in the nature of the organism. The more reproduction you have, the more potential variation you produce. It's self-produced. And the visual metaphor for that is this two-curve graph that Ed Wiley and I produced. That the growth of actual variation is less than the growth of potential. And all of this in here is everything that could be. This is the realm of adaptability. And it's huge, it's enormous. It's enormous enough that if you're a modeler and you want to simplify things, you could just say, oh, it's random. Everything's possible. It's like assuming instantaneous fixation and infinite population size. I mean, that doesn't happen in the real world, but population genetics modelers use those assumptions all the time so that they don't have to waste time having their computers run for 500 years. The origin of function space. This is the other sense of space in biology. Organisms impose themselves on their surroundings. The surroundings don't create them. And they don't mold them. Organisms impose themselves on their surroundings. That is what turns the surroundings into function space. The surroundings are not inherently anything with respect to biology until an organism does something to it. And that makes the surroundings, the environment, function space. Now that, the activity of organisms on their function space is to degrade their resources. So organisms actually have a net negative impact on the environment relative to themselves. They're not necessarily relative to other organisms, but relative to themselves. And that is what turns function space into fitness space. Because we're producing organisms very cheaply, they're all going after the same stuff, there's not enough of it there, you have this mismatch. Now, function space becomes fitness space. That's Darwin's necessary mismatch. That's how we turn the environment into fitness space. Organisms change the environment into function space. The overproduction of organisms by the nature of the organism turns function space into fitness space. Now we're going to do a little magic trick. I'm going to make the niche concept disappear in 2 slides. First is, organisms impose themselves on their environments, and as long as they're alive, they produce something analogous to a gravity well in space-time when a part of space-time is occupied by a body. But when that organism dies, its little gravity well in the function landscape disappears. It does not persist. Your niche does not persist beyond your life. However, if reproduction is so conservative that your offspring do the same thing you did and they replace you, it may fool biologists into thinking that there's something real about the space. But there's nothing real about the space. What is real is the replacement of dead organisms with offspring that do the same thing. That makes us think that there's something about the environment that's real. But in reality, what makes niches appear real is part of the nature of the organism. It has nothing to do with the environment. Organisms do not fill niches and they do not create niches. There are no niches. There's only life. There's only organisms trying to live by dealing with their environments. Now the dimensions of fitness, we still have fitness space, thank goodness. We may not have niches, but we still have fitness. The space in which organisms have non-zero fitness is fundamental fitness space, and then the part of that fundamental fitness space which is actually accessed by organisms is realized fitness space. So if you're an organism, if you're a species that lives only in the Amazon, you could potentially live in the Mekong River Delta of Southeast Asia, but you don't live there. So there is fundamental fitness space in Southeast Asia for you, but you're not there, so that's not part of your realized fitness space. And evolutionary lag load, that is Maynard Smith's term for the conservative nature of reproduction, provides a distinction between fundamental and realized niche space. which is proportional to selection strength. Natural selection is strongest in proportion to the degree of mismatch between organisms and their environments. The nature of fitness space. For maximal adaptive evolution to occur, fitness space has to be sloppy, not tightly optimized. And the concept of sloppy fitness space is something that was invented and proposed by a couple of people, including one former postdoc of mine, Sal Augusta. And that's because evolution is about survival. Darwinian evolution is about survival. It's not about winning. Spencerism was about winning. That's why Spencerism morphed into optimality theory. And John Maynard Smith spent his entire career talking about the fact that biologists should use optimality theory to understand why nothing in evolution is optimal. And finally, he just said, everybody wants it to be optimal, so I'm just not going to bother anything. But it's not about winning anything. If you are a Darwinian playing poker, you don't care about winning all the money. You just want to make sure that you're still at the table. Every hand, every hand, every hand. And Maynard Smith even proposed something he called the gambler's ruin. You can have 99.9% of all the money at the table, and 10 minutes later, you can have nothing. And that's the difference between Darwinism and neo-Darwinism. So here are a couple of cartoons that Sal produced about sloppy fitness space. So here you have a situation. Here's a geographical area. Okay? And inside that geographical area, you have a set of conditions where a particular species can live. And the dotted lines here, that's where the species lives. And in this particular situation, you've got that species is pegado right in the middle of its optimal environment. Here, you have the species living way out here, and most of the species is outside of the optimal environment. Only a little bit of it is in the optimal environment. So this is better adapted than that. What happens when the environment changes? This optimally adapted species goes extinct, and the less well-adapted species survives. That's the difference between Darwinism and Lamarckism. And that only happens if fitness space is sloppy. You don't have to have the maximum fitness, you only have to have non-zero fitness to survive. This population is fitter than that population. This population is going extinct if there's climate change. Down here, you have different geographical areas. Here's an area where the species lives right in the middle of its optimal environment. Here are 3 different geographical areas where the species is only found on the edges of its optimal environment. What happens if this area is wiped out by climate change? That species can still survive. Its fitness may be lower, but it will be there. It will survive. That's why fitness space has to be sloppy. It cannot be tightly optimized. Now, the final metaphor that I want to talk about today is complexity. Okay? And I'm going to ask the question, was Darwin's theory the first modern complexity theory? Was Darwin not 20 years ahead of his colleagues? Was he 100 years ahead of not only biology, but 100 years ahead of physics? And is that the reason so many people have tried to fix the theory, trying to make it more like other theories, because it was so far advanced? And this brings us to a paradox about complexity. Human beings are extremely good at recognizing complex patterns in nature. But in Western science, we have developed an entire intellectual tradition based on denying the existence of complexity. And I think that one of the reasons for this is because we've been lying to ourselves. We have been using magical thinking, even in science. Now here's a magical metaphor. It's called man the hunter. Now why do I call that a magical metaphor? Because it's not biological. We are not descended from predators. We have become hunters recently. But evolutionarily, we are not predators. We are not man the hunter by nature. We are man the hunted. And our ability to understand our surroundings and assess the complexity of our surroundings is exactly the kind of sensory modality you expect from prey items. You know the ecological saying, predators run for their dinner, prey run for their lives. That's just another way of saying this. And we're really good because we had to be. In order for us to survive, we had to be able to not just see the complexity of our surroundings, but to assess it accurately. Because if you underestimate the complexity of your surroundings, you get eaten. Oh, yesterday there were no predators, there were no lions at the watering hole, so there will never be lions there. Boom, your lunch. On the other hand, if you overestimate the complexity of your surroundings and you say, there was a lion there one time, so I'm never going there, you stay in your cave and you starve to death. So survival means that we had to be really, really accurate about our assessment of complexity. And yet, and evolution worked really well. I mean, we're really good at this. In fact, this piece of wetware is so much better than computers at detecting and assessing complex patterns that we had to invent an entire field, an entire type of computer programming to try to make computers do what we do better, called object-oriented programming. And the resolution of the paradox is, the reason we're afraid of complexity is because complexity was the part of the world that we could not predict. And so it became associated with fear, and then it became associated with evil, and that morphed in science into something bad. That is the error term in an analysis of variance model. Ooh, we don't want that. Get rid of that error. We're afraid of complexity because in our ancestry, that's where the boogeymen were. That's where the cave bears were. That's where the predators, that's where the diseases, the new diseases are. You wander into a piece of forest where nobody's ever been before, 2 weeks later, everybody is bleeding from every orifice and they die. That's complexity. That's why we're afraid of it. The complexity metaphor, and there are different ways to think of the complexity metaphor today, one of which is the tangled bank. Darwin's metaphor. Space and time, these two dualities of space and time colliding. Or expanding information space meets sloppy fitness space. And the dimensionality of the new tangled bank, if you have space and time interacting, you have information and function interacting in this large area, there's a lot of room for accommodation, for things to survive without being optimal. There's a lot of room for true creativity, and there's also space for localized optimization. And this is sort of the first attempt to try to visualize something about the space of evolutionary dynamics based on the transitions evolutionary perspective of Maynard Smith and Safari and the hierarchical view of Niles Eldredge, where you have temporal effects, you have spatial effects, and they interact so that you have evolutionary transitions based on information that can be easily accessed or not easily accessed. So common events, rare events. Some require special conditions to survive, some don't. And all of these evolutionary transitions have different time periods of significance and persistence. And this alone is enough to make the entire process extremely complicated and to generate enough dimensionality so that we have a lot of possibilities for survival. Even survival of a lot of the biosphere, no matter how much we screw the environment up ourselves. So back to the future. Darwin's theory was the first modern complexity theory, and the extended synthesis will be fundamentally Darwinian and not neo-Darwinian. And I want to then end with a couple of things. The cautionary metaphor, which says, and this is what I started with, the metaphor of the blind man and the elephant. This is not going to be solved by one person or one research group. The new evolutionary theory is going to require a lot of different people with a lot of different perspectives to do something that academics do not do very well, and that is cooperate with each other. Oops. Okay, so for example, in my case, this is just a very short list of the people who have most influenced me. And every one of these people stands for hundreds of colleagues and thousands of students that I've interacted with over 30 years. That's what I'm talking about. Now, fortunately, those of you in the audience who are young know how to network. And that's what it's going to take. And down here, of course, you'll see that these are scientists and philosophers, and these are poets, science fiction writers, and even musicians. Now, my question to leave you with this is, if Jimmy Buffett, who is an American rock and roll singer who lives in Key West, Florida, and whose most famous song is about drinking margaritas all day, if he understands this, why is this not well understood by professional evolutionary biologists? Thank you very much.
I think we got time for questions. A gente tem tempo para perguntas. Se vocês
I'm here for a month, so I have time.
Pode, quem não quiser falar inglês pode fazer português. A gente acho que arruma alguém para traduzir, ou ele provavelmente vai entender também.
That bad.
Shock.
There will be no examination.
Ninguém vai avaliar o inglês de ninguém.
So when you're proposing the fitness space, so basically you seem to think that there was this debate in ecology for a very long time if the nature is a product of the environment or of the organism, right?
Right.
So it seems that you think that in that case the fitness space would be the niche space being a product of the organism? Or
It's an emergent product of the organism, yeah. That's right. Well, all the organisms. But as Maynard Smith wrote in the 1970s, when you have a complex biosphere with many species, most of the environment for organisms is other organisms.
Right.
Okay? So there are two critical transitions in this. One is the origin of life, proto-life and life. You have what some people call the genetic takeover, the information takeover, where you go from replicators, chemical replicators, being completely controlled by the environmental conditions. You know, standard chemical reactions. If you don't have enough reacting coming in, everything stops. And the transition to autonomous replicators then changed the whole game. Because at that point, the replicators took what they wanted from the environment rather than just being informed by the environment. So that's one, and this is one of the reasons I have so much respect for Maynard Smith and Safmari's work. It's just, it focuses on the earliest events, the Big Bang of evolution, the origin of life, the origin of the genetic code, the origin of the cell, the origin of the eukaryote condition. I mean, 99% of the story of evolution happened in the first 5 or 6 of those major transitions, 3 billion years ago. That set up, that created a system that self-perpetuated. And once that happens, then you have a situation in which these living entities not only are relatively autonomous from their abiotic surroundings, but more and more of their surroundings become biotic. And you can see that in the transition from acellular to multicellular life. Okay? In a developing multicellular organism, by the time there are 4 cells, all of the environment for ontogeny is yourself. Which is to say, in the case of sexually reproducing organisms, which is to say, your mother's environment. And in the case of complex ecosystems, which you can think of as kind of analogous to a multicellular organism, most of the environment is not abiotic. Even many of the things we think of as abiotic, water and minerals and things like that, in complex modern ecosystems, most of that is recycled from organisms. So what life does is it elaborates its own environment. And that's another way of saying, yes, the niche space is created by life. And now the interesting thing to me about this is that if that's true, if organisms do two things, if in their behavior they degrade their own resource base, they cannot be constructing better niches for themselves. You can't, both of those can't be true. So the niche construction hypothesis fails on that account. However, if you do something that degrades your resource base, but in degrading your resource base, you create conditions that are better for some other species, and some other species, and some other species, and eventually that comes around to you, then you can see within a complex ecosystem that you can have these modifications that eventually make conditions better for you. But in order to do that, you have to invoke ecosystem level group selection. And you know how well that proposal is being received within ecology. Okay? Well, group selection is also something that is going to be a central part of the new evolutionary biology. Because one of the things we forgot, see, if it's all about winning, then it's all about conflict. And the winner is the optimal this, that, or the other. But suppose it's just about survival. If it's just about survival, then it turns out that you can afford to cooperate as long as the cost of cooperating is not great. And so the whole boogeyman about group selection turns out to be something that neo-Darwinism created. It was not inherent in Darwinism. There's no necessity for saying there cannot be group selection in Darwinism. In Darwinism, you say, okay, here are the conditions under which group selection would be okay. Let's see if it happens. And it turns out that just in the case of human beings cooperate all the time outside of their kin groups to ways that far exceed the expectations of population genetical theory. Organisms do this kind of thing all the time. And it's not always kin selection. There's a lot of group selection that goes on. Well, that only makes sense if evolution is not about conflict, but about conflict resolution. Okay? Now, how many in this audience believe in the endosymbiotic theory of the origin of the eukaryotic condition? You know, mitochondria were bacteria, chloroplasts were algae. How many believe that? I do. Okay, you all believe in group selection. Let's move on. Now let's talk about how much group selection we have, not whether or not it occurs. If you don't believe in group selection, then you give me a different theory for chloroplasts and mitochondria. Give me a different theory for hybridization in composites, if you're a botanist. See, this is an artificial conflict created by one theoretical framework. It's not something that has to be a conflict. Now, of course, there are people who love conflict. You know, there are people who really like the idea that there are going to be winners and losers out there. But my favorite evolutionary biologist is Urs Satmari. And one of the things that Urs says is, well, yes, genes are selfish. But fortunately, it doesn't matter. No, whichever.
So in that case, wouldn't you be talking about levels of selection? So wouldn't you be talking about...
Matos, mais lento, mais alto.
I'll repeat the...
Okay.
Yeah. I'll internalize it and then repeat it.
So would you be talking about the different level of selection? Then you have population level selection, species level selection, and then maybe ecosystem level selection?
Yeah.
Instead of group selection?
Not necessarily that hierarchical construction, but in the hierarchical construction that Niles Eldredge and his group have envisioned, where each of the major transitions in Maynard Smith and Satmari, for example, creates a new level of organization. And interestingly enough, that new level of organization also creates a new form of selection that's oriented right at that focal level. So for example, you have no sexual selection until there's sex. But as soon as you have sex, sexual selection appears. I mean, it happens that you get sexual selection as a byproduct of sex. So one of the reasons that Maynard Smith was always interested in the cost of sex as a theoretical issue was, you can't avoid sexual selection if you have sex. So what is the trade-off? What are the costs and benefits? Under what circumstances do the benefits of sex outweigh the costs? And the benefits of sex are things like increasing the efficiency of storing and transmitting information. Sexually reproducing species hold in their collective genomes a much more potential than asexual clonal lineages. However, sexually reproducing populations and species are susceptible to sexual selection, which can be an additional bottleneck which restricts variation, costs and benefits. But that's part of this view, is that every time you have a new level, a new hierarchical level of organization emerge, you automatically get a form of selection that's focused on that in particular. You don't escape the other forms of selection, but you get this also. So yeah, that's absolutely part of it. Yeah, I agree. You had a question?
First of all, thank you for coming. It's really rewarding for everyone.
Thank you. That's very nice.
I have seen that we are never getting far from the second law of thermodynamics. Life is an open thermodynamic system, and as you said, we are not. This is not about winning; it's about survival. So, how do you see the competition, the theory of competition?
That's an excellent question. Yeah. There are two levels to answer that question. The first is that if you want to think of this strictly in terms of efficiency, either information or energy, and they're interchangeable. So either information storage efficiency or energy use efficiency, it's the same thing. When there is a competition, the more efficient will win. However, there is an additional component to that, because you then have to ask whether evolution is about conflict and winners, or if it's about conflict and resolution of conflict. So in Maynard Smith and Safmari's original book, it's all about conflict, but it's all about conflict resolution. And the conflict is resolved by division of labor. Okay? Suppose you have an asexually reproducing clone of protists. You have cell division, you have two individuals, they go off and they disperse maximally unless they have to be crowded together and then they compete. But normally they move off and do their own thing. What happens if you evolve an innovation in which the cells stick together after they divide? They cannot escape. You either have conflict, in which case most of the cells kill each other off because they can't escape from each other, or you have conflict resolution, division of labor, specialization, and complex multicellular organisms. So how do cells in a developing human being keep from competing with each other? Some become liver, some become stomach, some become muscles, some become skeletons, some become bones. So that's again, this is very metaphorical, and I don't mean to do injustice to Evo-Devo people in the audience. I know it's more complicated than that. But in evolutionary terms, if I want to talk to an Evo-Devo person and a population geneticist, that's the language I use. It's the language of conflict resolution. And that's why Maynard Smith and Safmari talked so much about division of labor. So there are two senses in which competition is still central to our thinking about what happens. One is in the traditional sense of if you have 5 sandwiches and 10 people, the first 5 that get a sandwich are going to survive, and the other 5 will starve to death. But then there's a deeper, more important sense that those 10 people will survive longer if they share the sandwiches. Yeah.
You said about we have this endless room for variation and evolution is going on all the time, but we are seeing now that we're losing species and we are not seeing much species being created. So speciation is not, we don't have see many chances for species. And how this matches with that timeline? I think maybe our linear timeline is getting shorter and we have more like the circular system. So we're just evolving what's here and surviving what's here, and we're not, so we are simplifying the world.
Yeah, that's a really important thing. One of the reasons that it's important to think of the production of potential as being part of the nature of the organism is that helps us explain the pattern, and this is why one of the reasons Niles Eldredge is the real authority on these patterns is because he's a paleontologist. And paleontologists know what has happened to this planet every time there has been a major climate change event. The good news is that in the past, for every climate change event in the past, even the ones that destroyed 95% of the species on this planet, within 20 million years after that event, the whole world was full of life. Not the same life never comes back. But within each surviving species, you have this dynamic of indefinite, open-ended variation, production of variation. So what we can predict is, so long as we don't destroy all life on this planet, something will come back and produce a new biosphere. It won't be the same biosphere ever again, but life will continue. So the reality is, when we talk about species extinctions, yes, that's a net loss of existing information, but that doesn't mean that we've lost capacity to produce information. We've lost the capacity to produce this information. But there are other possibilities. But as well, if we talk about climate change, biodiversity crisis, emerging diseases, right now we have sociologically and politically, we have the environmentalists and the developers. And all they do is fight. And you can get lots and lots of money to have conferences where you fight with each other. It's conflict, no conflict resolution. What is the common ground? Okay, every environmentalist on this planet uses the internet. Everybody uses high technology. Nobody wants that to go away. The paleontologists tell us that the species that survive major climate change events are species that have large populations distributed over a great geographical area. What does that mean? It means Homo sapiens is not going to go extinct. This is what could go extinct. My great-grandchildren could come up to my granddaughter and say, "What kind of fish do you catch with an internet?" Because they will have never known anything like electricity or computers. That's what we're all trying to save. The reality is that the common ground for everybody is the desire for technological humanity to survive. And whether it's we want them to survive so we can make lots of money, or we want them to survive so that we can enjoy the natural world, it doesn't matter what your motivation is. We have a common interest in trying to preserve this. That's conflict resolution as opposed to conflict. That's a Darwinian perspective rather than the neo-Darwinian perspective. Now, when President Obama recently accused the Republicans of having a social Darwinian or a social Darwinist approach, in fact, he was making the mistake most of us have made for 50 years. What he's talking about is a social neo-Darwinist program. A conflict, conflict, conflict until I'm the only one left. It's not a Darwinian program. A Darwinian social program says, how can we all survive? How can we minimize our losses? How can we cooperate? How can we all get something out of this? Now, of course, organisms are not saying, how can I survive with my neighbors? But it's trivially true. We know in parasitology. What is a good parasite? A good parasite is one that is invisible, causes no disease. The host doesn't even know it's there. And most little children on this planet, you don't know that they have pinworms unless they're doing this when they're walking across. Oh, okay, they've got pinworms. But otherwise, it's invisible. That's a good parasite. There's a lot of conflict resolution there. I'm okay, you're okay, let's evolve. And that happens through a lot of trial and error. I mean, there's a lot of competition, there's a lot of mistakes, but the end product, these successful associations that we see, involve conflict resolution, they involve division of labor, they involve mutually interacting specializations. And so, so I recommend Maynard Smith and Sathmar as the major transitions in evolution. And a new edition will be coming out soon. Ursh is just about finished with it. But you talk about things, for example, the difference between DNA and RNA. Now, RNA is a good metabolic molecule, and it's a good information molecule. DNA is a terrible metabolic molecule, but it's a better information molecule than RNA. The problem with DNA is that DNA is hydrophobic. So reactions that produce RNA and DNA, the DNA will disintegrate if that's in an aqueous solution. If you somehow can get RNA replicating inside a lipid membrane, then one of the mutational byproducts of RNA replication is DNA. And inside an environment, the DNA can survive. And at that point, its better replicative functions take over. And the RNA's better metabolic functions take over. And you end up with a really robust form of life. And that's one of Maynard Smith and Sathmar's transitions. And that's a really fundamental transition. That is something that is ancient in evolution, and something that no amount of natural selection is going to change. That's something that life did to itself. And it may have been an accident. It wasn't necessarily inevitable, but we know how it worked and why it works. But these are fundamental cases of division of labor and cooperation and conflict resolution in the earliest aspects of life. There's probably a little more complicated answer than you wanted.
Alguma pergunta mais? Vamos, acho que a gente agradecer a presença do professor. Eu não sei se alguém tem mais pergunta. Alguém tem mais pergunta? Última vez. Okay. So thank you, Dave, for your presentation.
Muito obrigado.